Welcome all. So, we will take up from where we left in the last lecture. We are doing the examples relating to the pressure impulse diagram. We did 2 examples and today we will continue with the rest of them. So, let us dive down. So, we are looking into the example 3. Okay. So, in the example 3 it is said that brick wall will survive if the impulse is less than the 600 kPa. Okay, times kPa milliseconds. Okay. So, 50 kg of TNT detonation produces an impulse of 1200 kPa milliseconds at 10 meter along on the side on direction. Okay. Assuming that the impulse is inversely proportional to the square of the standoff distance, we need to estimate the safe standoff survival. Okay. So, the survival limit is been given, okay, and the case of the applied loading is also given. Okay. So, we need to estimate the safe standoff distance, that is this much, okay, for this particular case. So, the impulse is 1200, the magnitude of the impulse is 1200, okay. It is occurring at distance of 10 meter. Okay. We have assumed that the impulse is inversely proportional to the square of the standoff distance. Okay. So, impulse is inversely proportional to the square of the standoff distance, okay, and the safe quantity is 600. Okay. So, we formulate this equation, okay, and here we evaluate that if the standoff distance is more than 14.414 meter, then the structure is going to be safe. Okay. Next example. Okay. So, in this case a light framed industrial shed. Okay. For the case of a light framed industrial shed, okay, let us say that this is our shed. Okay. This is an industrial shed. A calibrated collapse boundary, okay, for a given failure mode is approximated by p plus 1. It means that in this asymptotic curve, okay, the equation for this curve is given by this one. Okay. So, if it is more than this region, the collapse will occur. If it is less than this region, no collapse will occur. Okay. And this is the equation of this collapse boundary. Okay. And the structure is my industrial shed like this. Okay. The magnitude of the loading is given as the maximum triangular pulse has a magnitude of 100 kPa, time is 25 milliseconds. So, if this occurs, okay, what will happen to my structure? Okay. So, I have my pressure quantity, I have my time period quantity, then we calculate our impulse quantity, okay, and then we put into the given equation. Okay. And if I put into the given equation, my structure is falling less than this, in the less than the periphery of the boundary. Okay. So, the value is 0.812 to be precise. Okay. So, since this value is less than the collapse equation, then there will be no collapse in the structure remains safe, okay, or even if some damage has occurred, it will not collapse. Okay. Moving ahead, next example. So, we covered 4 examples and now we are going to see the influence of the load and structure properties on the PI diagram. Okay. So, we will see the effect of the pulse shape. Okay. So, here as we transition in the 3 regions, okay, if we break down into these 3 regions again, the impulsive region, the dynamic region and the quasi-static region. Okay. And here we have seen that once the pulse occurs, okay, the structural response has just begun to occur or the maximum response will occur way after this point. Okay. In this region both are comparable, okay, and the structural response will occur, okay, comparable to the loading duration. Okay. And in this one the loading is occurring and the response has already occurred, it has attained its maximum value. Okay. So, effect of the pulse shape. So, asymptotes impulsive and quasi-static, they will remain unchanged. Okay. The shape of the pulse. Okay. So, here due to the shape of this pulse, okay, due to this shape the asymptotes will remain unchanged. Okay. The effect in the transition remains, it will depend upon the pulse type. Okay. So, again the influence of the rise time. We have seen earlier that the actual blast loading occurs like this, okay. But since the rise time is in nanoseconds, okay, we neglect the effect, okay. So, we normally consider it as like this only. So, here we are looking into the effect of the rise time on the response of the system, okay. So, the finite rise time alters the PI curve shape, okay. If the rise time is comparable with the total load duration, okay, if this time is comparable with the loading duration, then it will have an influence on the PI curve, okay. The impulsive response will remain unaffected, okay. In this region the effect will be less. There will be a great fluctuation on the quasi-static response, okay, depending upon the rise time to the loading duration, okay. So, here we can see there will be a fluctuations in the quasi-static regime, okay. So, the quasi-static asymptote will shift from 0.5 to 1, okay. So, earlier we see that it was asymptote to 0.5, here now it will be asymptotic to 1, okay. So, since it is a slow application, there will be no dynamic amplification, okay. So, the quasi-static asymptote when equal to 1 is equivalent to a static loading, okay. So, it will become equivalent to a static loading, okay. The influence of the damping, okay. Higher damping will increase asymptotic values, okay. It will try to die out first, okay. So, this asymptotic value depending upon the dynamic factors, okay, will try to die out first, okay. So, if this is no damping and this is significant damping, so then we can see the variation of the PI diagram, the variation in the region depending upon the increase in the damping, okay. Ductility, okay. So, higher ductility ratio, if the ductility of the system is large, okay, it will lead to a safer region, okay. So, here we can see the ductility is 1, okay, the region is towards the left, okay. It means that if we construct it, okay, if we construct the diagram and if the ductility ratio is less, okay, if it is let us say elastic only, okay, okay, then this curve, okay, here it will collapse, here it will not collapse, okay. And as we increase the ductility, this region shifts upwards, okay. So, there is a greater margin of the structure to behave in a safer fashion, okay. So, ductility basically shifts the failure threshold outward, okay. There is more inherent resistance in the system, okay. So, ductility basically a good thing in the blast cases, okay. So, applications of all this study, okay. So, we can apply this thing for a preliminary design, okay. In the preliminary design, the PI diagrams are a fundamental tool for the initial design stages of the structure that might be exposed to blast, okay. So, this gives us an initial estimate of the region, okay, the region in which the structure will collapse or it will remain safe, okay. Damage assessment, okay, that helps to determine the damage of the structure, okay, under different blast scenarios, okay, under the different impulses, different magnitude of impulses, different time duration, we can assess what will be the damage state of the structure, okay. So, both this diagram together, okay, gives us a curve in which we can plot out whether the structure will be damaged or it will not be damaged, okay. So, if we know the damage criteria based on the PN diagram, we can determine the appropriate distance, okay, to ensure the safety, okay. As we have seen in the one of the examples, okay, we could assess the safe distance for the structure depending upon the damage curve and the given intensity of blast, we can calculate the safe distance. Then comes the human injury criteria or the HIC criteria, okay. So, the human organs like lungs, eardrums, head, okay, different things are subjected to the blast loading, okay, and they respond mechanically to the blast loading, okay. and these systems can be modeled using a PI diagram. Okay. And these PI diagrams, okay, they were used to assess the human response to the blast loading and to establish a damage criteria for a specific organ. Okay. So, if we take the different organs, we can calculate the safe criteria for these different organs. Okay. So, this PI diagram has a wide applications, okay, in the design of the structures. Okay. So, now we will move further ahead and we will talk about the dynamic response of a single degree of freedom system applied to my different structures. Okay. So, now we will be dealing with the dynamic response and single degree of freedom analysis. Okay. So, earlier we had a small understanding of the single degree of freedom system. We will have a quick recap, okay, and we will see how the system behaves during a when applied by a dynamic system. Okay. So, we take the simplest of the system. We take this type of system in which we have a mass, okay, that is represented at a rigid body. We have a stiffness, okay, and the system is on a roller. Okay. Okay. There is no friction applied to the system, and this is the degree of freedom of the structure that allows it to move in the horizontal direction. Okay. So, the system is going to move back and forth and back and forth. So, this may be due to an initial condition, okay, or due to an application of the forcing function. Okay. So, when this happens, okay, what are the forces that are acting on the system? Okay. If you look into the D'Alembert principle, the pseudo acceleration will be acting, okay, and it will form the inertial forces. Then the stiffness will be acting on the system, and there will be a damping on the system that will be acting, and a forcing function will act on the structure. Okay. And this is the chosen degree of freedom. So, the total equation of motion will be okay. So, here now we are ignoring the damping, okay, and forcing function we are also ignoring. Okay. We are saying that the system is going to behave due to its inertia effect and due to its stiffness effect, okay, due to its inertia and stiffness only, and there will be an initial velocity or there will be an initial displacement in the structure. Okay. So, this becomes my equation of motion. Okay. So, the solution of the equation of motion is given by this equation, and depending upon my initial conditions, initial displacement and initial velocity, this is the total response of the system. Okay. So, this is the total response of the system. Okay. Here the initial displacement is being shown, and this is the initial velocity, and the system is going to oscillate. Okay. So, this is the motion of the system back and forth, and this is how it is going to do. Okay. So, this is the representation of the total motion of the system, which is given by this curve also. Okay. And we can write down the amplitude of this curve and the phase angle of this curve. Okay. So, this is the representation of the single degree of system vibrating, okay, with just an initial condition. Okay. So, moving ahead, now we have introduced a damping in the system. Okay. So, earlier we saw what was happening in my system. So, there was an initial displacement or initial velocity. So, depending upon that, my system was going to oscillate like this, okay, and this magnitude was constant. Okay. So, if we introduce a damping in my system, now what is going to happen is that this response is going to decay. Okay. So, there will be a decay in this response, okay, which is shown by this curve out here. Okay. So, there will be a typical decay in the system response, okay, and depending upon the ratio of the damping, okay, ratio of the damping C applied to C critical, okay, that is defined as the damping ratio. Okay. So, depending upon this damping ratio value, okay, my system can be, if it is equal to 1, it is critically damped, less than 1 under damped, greater than 1 over damped. Okay. So, less than 1 it will try to oscillate, but it will eventually die down. Okay. Greater than 1 it will just die down. Okay. So, this is how the system is going to behave depending upon the inertia of the system, the damping of the system and the stiffness of the system. Here the system, there is no external load, only the initial velocity or initial displacement has been given to the system. Okay. So, here we are seeing the effect of the different damping ratios. Okay. If damping ratio is less than 1, here we can see this is oscillating, but this is eventually going to die down. Okay. Means this thing is happening to my system. Okay. If it is critically damp, this one will die like this, and if it is over damped, it means that damping applied to the critical damping is greater than 1, then the system will die down asymptotically. Okay. So, this is the response of the single degree of freedom system. Single degree of freedom system means that there is only one degree of freedom. Okay. Here this is the only 1 degree of freedom. Okay. The system can oscillate in this fashion only. Okay. Okay. So, these are the undamped system, okay, and these are the underdamped system. Undamped system means C equals to 0. Underdamped systems means the ratio of C applied to CR, that is zeta, that is less than 1. Okay. So, response of the two types of system. Okay. Moving ahead. Okay. So, now we are introducing the forcing function in my system. Okay. So, let us say a forcing function, a sinusoidal harmonic function is being applied to the system. So, the response of the system u or x, okay, whatever you want to call it, it will be due to two parts, okay, the steady state and the transient response. So, these are the transient response, and there will be a steady state response that will be a function of the applied loading, okay, applied loading by stiffness somehow. Okay. So, all the systems response, the total systems response will be a combination of the transient and the steady state response. Okay. So, this is the response of a single degree of system, okay, subjected to a sinusoidal type of loading. Okay. Okay. So, if you look, if the sinusoidal loading is there, okay, the total response, as we said earlier, will comprise of plus, okay. So, there will be a signature comprising upon the nature of the system, and there will be a signature comprising upon the nature of the external loading. So, this is the external loading nature, and this is the nature of the system. Okay. So, it will have two frequencies, okay, omega n of the system and omega of the external applied loading. Okay. So, this total response, okay, is given by this external curve. Okay. Okay. And this part is the steady state response curve. Okay. So, this part is from this external forcing only, and these oscillations, okay, are occurring due to the oscillations in the structure, and since damping is applied, this oscillations, okay, if I can plot the asymptotic lines out here, okay, I will see that this will eventually die down. Okay. Okay. So, here we can see the system responses, okay, eventually die down due to the presence of the damping. Okay. So, the transients will die down. Okay. So, these are called the transients, and the steady state, okay, the response due to the external forces will be the only remaining part after significant amount of time. Okay. So, one part is showing the response of the system, and the other part is showing the response of the system due to the externally applied load. Okay. So, the steady state response is due to the externally applied load, and this is the transient nature, the oscillations, okay, these oscillations that are continuing due to the system responses. Okay. Okay. So, formulating the equation of the motion. So, what we have done now, what we are going to see is, we are going to see an actual system. Okay. Let us say we have taken a cantilever bar. Okay. So, when we have taken a cantilever bar, we are taking a bar with a uniform cross section. Okay. The cross section is uniform, material is same. Okay. So, the material is not changing. Okay. And let us say the modulus velocity of the material is A. Okay. And let us say that we are going to see the vibration of the system, okay, in the axial direction only, and this is an load applied. Okay. So, theoretically there are infinite numbers of degrees of freedom. Okay. If we want to determine the exact response of the system at any given given instant of time, we need the information about all these axial responses. Okay. So, this independent axial responses, okay, this independent quantity of axial responses are called degrees of freedom. Okay. So, for any given system we theoretically have infinite number of degrees of freedom. Okay. Okay. So, what we can do is we can divide into a finite number of sections. Okay. And we can divide it into a very fine number of sections, and then we will see that we need so many, we can divide it into so many pieces. Okay. And we assume that the displacement of all points within the section are same as the center of that particular section. Okay. Okay. So, now what we are trying to do is that we are trying to divide the bars into n number of sections, okay, such that this small length is total number of total length divided by the number of sections. Okay. And if we can squeeze it n to infinity, okay, we will obtain what is known as the differential section. Okay. So, the number of displacement coordinates to analyze the model completely is equal to the number of degrees of freedom. Okay. And when n is going to when n is very great, it means we will have greater accuracy. It means that we need the pieces of information to be infinite. Okay. Okay. So, what we can do is that we can also replace the displacement of the rod, okay, using a shape functions and a time dependent part. Okay. So, the total displacement of the system can be broken down into two parts. Okay. One is the shape of the response and other is the time dependent factor. Okay. So, one is the shape that depends upon the length, and the total response, okay, along the length is a function of these two quantities. So, z is a function of time and xi is a function of the spatial coordinate along x, also called the shape functions. Okay. This is how the system is going to behave during a dynamic event. Okay. This is how basically it is going to oscillate. So, if we choose the appropriate shape function, the only unknown is the time dependent coordinate, okay, and the system will reduce to a single degree of freedom system. Okay. So, the inertia and the spring forces acting on a small section of the rod are given by, this is the inertial component, okay, okay, and this is the stiffness component. Okay. So, inertial component is nothing but mass per unit length. Okay. Here we had mass per unit length. So, the total mass of the system will be mass per unit length times the length times the acceleration of the system at that particular point. Okay. So, mass per unit length times the length times the acceleration component, and acceleration component again is broken down into these two components. Okay. Similarly, the stiffness component, so stiffness EA, okay, we are now assuming the cross section to be varying, okay, times the change in length. Okay. So, this equation is giving my the first one is giving my the inertial component and the second one is giving my the stiffness component. Okay. Okay. So, we apply an virtual displacement to the rod. Okay. So, the elongation of the small section due to the virtual displacement is this much. Okay. So, now the virtual load done by the elastic spring is given by this equation, and substituting this to value we get the total work, okay, and the external forces are body force due to inertia and the tip of the forces. The virtual work done by this forces again is given by this equation, okay. And then when we set up the system such that the total external virtual work must be equal to the virtual work done on the internal elements, okay. So, the total external external virtual work component, we are equating with the virtual work done by the internal elements. So, when we are equating these two equations, we get the what we know as the generalized mass, generalized stiffness and the generalized forces. Okay. So, m star, k star and p star. Okay. So, this is the general force, okay. This is the generalized stiffness or the generalized mass, or we can call it as the equivalent mass also, equivalent stiffness also and equivalent force also. Okay. Okay. So, same thing we can do for a flexure type of problem also. Okay. For this flexure type of problem, this will be the equation of motion, okay. And here we are assuming that my ground is moving. Okay. So, this is for a specific case where there is a ground movement. Okay. We can take the UDL, externally applied UDL also. Okay. So, we can change this force depending upon the how the load is being applied. Okay. So, if you leave this portion out, okay, this will remain same. Okay. For a flexure type of problem, okay, this will be the equivalent mass or m star, okay, and this will be the equivalent stiffness or k star, and the forcing function f, okay, depending upon how is applied as a ground displacement or as a uniformly distributed load, then we can have the equivalent equation for the forcing function also. Okay. So, what are the requirements for the shape function? Okay. The selected shape function, it should satisfy boundary condition of the system. Okay. So, let us say we have this is my system, this is a cantilever type of system. Okay. So, the boundary condition out here are the displacement, okay, is 0, okay, and for this particular case the rotation is also 0. So, we have to choose a shape function which mimics this boundary condition. Okay. So, the easiest way is to take the displacement equation, okay, for this particular cantilever. Okay. We know that displacement equation for this particular cantilever, and we can normalize it, okay, with the required degree of freedom. Okay. Let us say we have to calculate the maximum displacement at this point. Okay. So, we normalize it with the maximum displacement, maximum static displacement at this point, or if we have to calculate the displacement at x along the half of the length, okay, then we can normalize it using the half of the length. Okay. For the similarly for the beam case also, okay, if we have to take a simply supported beam, okay, so this shape functions, okay, we can easily take the shape functions as the vertical displacement equation. Okay. We can take the vertical displacement equation and we can use the vertical displacement equation, okay, as the numerator of the shape function, okay, and we can normalize the value, okay, of this equation with wherever we want to calculate my degree of freedom. Okay. If I want to calculate at y max at x equals to 2, at x equals to L over 2, okay. If I want to calculate the degree, if my chosen degree of freedom is at the halfway midway point, then I normalize it by y max, where y max is calculated at x equals to L over 2. If it is L over 4, I can calculate at L over 4 the maximum vertical deflection at wherever my point is required. Okay. So, this way I can choose the shape functions depending upon my static knowledge that I already have. Okay. So, this is how I can select the shape function. Okay. The boundary conditions, they fall essentially into two categories. Okay. They are the essential geometric and the natural boundary conditions. Okay. For example, for a simply supported beam, the two essential boundary conditions specify deflection of beam should be 0 at the two ends. Okay. Simply the deflection at two ends will be 0. The natural boundary conditions specify 0 moments at the two ends. Okay. So, the essential condition or the geometric condition is that the deflection at the two ends should be 0. Okay. Natural boundary condition is that the moments at the two ends are 0. Okay. The shape function should at least satisfy the geometric boundary condition. Okay. The shape function has to satisfy the geometric boundary condition. Okay. the shape functions and its derivative should satisfy certain conditions of continuity and differentiability. Okay. For example, for a flexural vibration of the beam, the highest derivative appearing in the virtual work or generalized term is of the order 2. Okay. So, those two terms should be differentiable. So, as such the shape function should be twice differentiable, okay, which also implies that the first derivative should be continuous over the length of the beam. Okay. It means this, in this case the first derivative, okay, that will be the rotation, it should be the continuous over the entire length of the beam. Okay. So, with these constraints a variety of shape functions can be chosen. Okay. One possibility is to determine the shape functions as the deflection of the structure due to some static force, okay, the same thing that we have discussed right now. Okay. So, the easiest one is to take the deflections of the structure due to the equivalent static force which is producing the same shape function. Okay. Okay. So, we can take one example. So, we take a uniform simply supported beam of mass m, okay, and it supports a point mass at the center. Okay. So, what we are trying to do is that we are trying to obtain the equation of motion. Okay. So, what we have done here is that since this was a simply supported beam, what first we did was we took out the beam, okay, and we put a static load. Okay. From the static load we can calculate the end forces, okay, and if we cut at any particular piece, okay, we can calculate the internal forces. Okay. We can calculate all the internal forces, and if I can calculate the internal forces, I can calculate the bending moment. Okay. So, bending moment will be, and using the Bernoulli's equation, I can put it here, and this is valid from 0 to, okay, I can calculate the deflection. Okay. So, I can calculate the deflection equation. Okay. So, this is the new, so xi, so this if deflection equation becomes the numerator part. Okay. And if I want to calculate, okay, let us say I want to calculate the deflection at the center. Okay. So, here the mass is located at the center. Okay. So, if I choose my degree of freedom as vertical displacement at center or at x equals to L divided by 2, I can, this becomes my numerator. So, the denominator will be this y calculated at x equals to L over 2, and this becomes my shape function. Okay. So, this is the shape function that is being used out here. Okay. And here we can see xi at L over 2 becomes 1, it means that the chosen degree of freedom is at the center. Okay. So, this is how we can calculate the shape function. Okay. Once we have the shape function, okay, once we have the shape functions, we can calculate the total mass of the, or the equivalent mass of the system. The equivalent mass of the system will be m. Okay. So, this is due to the distributed mass. So, this term is due to the distributed mass of the system, plus at the center there is a concentrated mass. Okay. So, this part is due to the distributed part, okay, and this part is due to the concentrated mass. Okay. So, now we will look at this term again very closely. Okay. So, we break down this thing into two pieces. Okay. One is the concentrated mass at the center. Okay. So, since it is located at the center and we are calculating my degree of freedom, okay, or the vertical deflection at the center only. So, this entire mass will come here. So, it will be multiplied by 1. So, its contribution is m. Here let us look into this term. This is approximately half of the total distributed mass. Okay. So, if we take that beam, okay, and if we break the beam into two parts, okay, okay. So, if you are discretizing it like this, okay. So, this was a continuous approximation. I will try to look into a discrete approximation. So, here this piece has mass m divided by 2, this piece has mass m divided by 2, and if you want to discretize it, okay, into this 4 regions. Okay. So, here it will be m divided by 4, m divided by 4, m divided by 4, m divided by 4. Okay. So, at the ends the contribution of this mass will be 0, contribution of this mass will be 0, and the center, the contribution of this mass is m divided by 2, okay, that is 0.5 m. So, using this approximation also we can write down. Okay. So, this is slightly less than 0.5, it is approximately 0.48 and this is approximately 0.5, and remember all these things are approximations. Okay. So, here we are approximating the equivalent mass. Okay. So, this is m star or m equivalent. Okay. Similarly, using the equation we can also calculate the equivalent stiffness. Okay. K equals to 0 to L EI square x, okay, integrated over the entire equation. Okay. The previous equations that we have developed before, or we can use our static knowledge. Okay. The stiffness, okay, so that we have defined stiffness as the amount of force required to cause a unit deflection. Okay. So, the unit deflection at the center due to a load P is the deflection equals to P L cube over 48 EI. Okay. So, if I rearrange this thing 48 EI over L cube times delta equals to P. So, the amount of force required to cause a unit deformation is my stiffness. So, the amount of force required, okay, if I write it using Ke to cause a unit deformation is my stiffness. Okay. So, Ke becomes 48 EI, which is again given out here. Okay. And this way we can calculate the equation of motion. Okay. So, using this example we can see how we can calculate the equivalent mass, equivalent stiffness and formulate our equation of motion, okay, for a chosen degree of freedom. Here when we started the problem, we started with the choice of the degree of freedom as the vertical displacement at this point. Okay. So, depending upon the choice of the degree of freedom, these equations will be changed. Okay. So, here we saw when we were calculating the zeta, in the denominator will be the deflection at the chosen degree of freedom. Okay. And when we calculated the stiffness also, the deflection point, okay, either using the zeta case or even if we use the amount of deflection, the unit deflection, okay, that will be at the point of chosen degree of freedom. Okay. So, whenever we are calculating our equivalent mass or equivalent stiffness, we will always calculate with respect to the chosen degree of freedom. Okay. So, with this I will stop here. Thank you.